Afternoon, everyone. Welcome to our NITheCS October Mini-School. My name is Francesco Petruccione. I'm the interim director of NITheCS. And today it's a really great pleasure to be able to introduce to you Henri Laurie. Dr. Laurie is an applied mathematician who recently retired from UCT, but is still very active. And he has a very interesting career path because he started his academic endeavor studying arts. And then he bumped into formal logic and ended up being an applied mathematician studying population dynamics and other things. Yeah? And I was introduced to Henri because he's an expert in Julia, yeah, and I think he likes very much open source and text-based editors and things like that. So it's completely up my alley. Yeah. So Henri, people are here to listen to you. We are all very keen, and I'm personally very interested in learning more about Julia because I recently learned how fast it is. And I love the fact that you can name variable with Greek symbols. Yeah, that's the killer application for me. Yeah. So Henri, please, over to you. And sorry, maybe while you share the screen or whatever, I remind the participants to use the Q&A to ask questions, and maybe at the end we can ask people to raise their hand and we can give you the opportunity to ask questions in person. Yeah. So please,
okay.
Over to you. Yeah.
Okay. So yeah, please ask questions or make comments, and the coordinators will tell me about it. So I'm also, I started using Julia because I was intrigued by the speed, and I was very frustrated by some simulations I was doing. This phrase, easy, generic, fast, is taken from what some of the founders of Julia have been saying, not really at the beginning, but in more recent years, where the ease of Julia is what one finds in many dynamic languages, but it is a very generic as well. I mean, many languages are in many ways generic, but in Julia, it's kind of obligatory to be generic. But nevertheless, these two features were usually thought to mean that it cannot be fast, but Julia has actually found a way, the designers of Julia have found a way to do that. And I want to emphasize that. And but also I want to acknowledge that you pay for that in some ways for the combination. So in these 4 seminars, today I'm just going to showcase Julia. So there are some things that people working in Julia can justifiably be proud of. And of course, one of them is speed, but there are a number of others. I find Julia a very charming language to write. It's not merely easy to write. There's something quite beguiling about the code patterns in Julia and the syntax. And then I also want to just highlight the quality of Julia's resources, and finally reflect on some aspects where things in Julia are either unavoidably slightly problematic, or else they haven't yet caught up with what Julia can be. And then next week, I want to talk in more detail about the structure of the language, the design principles, the trade-offs, and how what they were decided on, and go into more detail of some of how the components of Julia interact and work together. This then comes together for me in differential equations. This is a meta package. There are very many packages that are part of differential equations. And differential equations itself is now part of a bigger project that also comprises machine learning. But it's my opinion that differentialequations.jl is now best in class for general purpose differential equation solving. Of course, for special purposes, one will usually be able to beat it, but I don't think you can beat it by far. It's not only is it very, very good in almost everything, but there is nothing, as far as I can tell, that it is really bad at. And then on the 28th, I want to return to the question of the two-language problem and the expression problem and what those mean. I will not go into detail in them today, but I will just mention them. And then work out whether, well, not work out, I guess, but just give some reflections on Julia for HPC and a number of recent developments that certainly maintain Julia's promise. Okay, so today I want to talk about the reasons why Julia was developed and what the founders say about it, the aspects of what Julia is what they can be proud of, the charm, the community and resource of the gotchas. I've already outlined those, so let me go on. So why was Julia created? So Julia dates the initial meetings and coding that led to the very first components of Julia come from 2009. And there are quite a few public and charming questions. So there's this this blog, and it's quite nice to look at. So let me see if I can pull it up. Now, okay, I'm not really going to. They just say we are ambitious. We love MATLAB, we love Python, we love C++, we love Perl, and we want all of those in one language, all of those features. There's a talk of similar vintage where you can watch them talk about the early stages of the language. This is when Julia was first publicly announced. So that's about 3 years after Julia started. And then this 2015 paper talks about also Julia relatively early on. And in fact, this one, oh, sorry, then there's a podcast that talks about the early history. But really, this is the reason. We have interactive dynamism and high performance. So that was the ambition of Julia from the start, and to a large extent, it delivers. So the four founders had interesting overlapping careers, to some extent via MIT, to some extent by a company that Edelman was, where Edelman was a professor, is a professor at MIT. And he also was a founder of a company called Interactive Supercomputing. And Bezinson and Shah started working at that company, and Karpinski and Shah had been students together. So there's a combination of research and commercial computing and university work that brings them all together. I don't know how long it took before they were all in the very same place, but they certainly weren't in one physical proximity to each other at the beginning. And they had slightly different motivations. Bezinson had played with parsers and lib and trying to write computer languages. Edelman was a very well-regarded researcher in supercomputing, linear algebra, and had developed a way of parallelizing MATLAB. Karpinski and Shah were people who were employed to do lots of scientific computing and had a lot of experience of frustration with the many languages. So although they were very pleased with the interactive environments like MATLAB, Python, and R, they were also very competent and appreciated the speed and the fine-grained control that you get in the statically compiled languages. I do want to see if I can just show you this. I want to share just a why we created Julia. Okay, let me show. Let's go to this one. Okay, so this is 2015, probably written around 2014. So it's in the early stages, and they are emphasizing multiple dispatch, and they're emphasizing their breaking of these constraints that were very widely accepted at the time. You have to prototype in one language and then rewrite in another language. They came to use the term two-language problem, and I'll get back to that word. Okay. Right, so I hope this is still working. So this is the old way. If you want to work in computing and you're dealing with a relatively large scientific problems, then what you do is you write specialized code, pieces of code from many languages. They're very powerful. Many times you don't even have to write them. You can just find them. And then you glue them together with some kind of mechanism for gluing these things together. And this was actually already identified and seriously proposed as best practice by Oosterhout in 1998. This is from the abstract. It says now 1998, people are moving away from system programming languages towards scripting languages, and makes the prediction that scripting languages will handle many of the programming tasks better than system programming languages. And I think that by and large turned out to be true. The system programming languages, Oosterhout claims, were designed for building data structures and algorithms from scratch. So that's the crucial term. And starts the most primitive computer elements. And then scripting languages, according to Oosterhout, are designed for gluing, and they assume the existence of a set of powerful components and are intended primarily for connecting the components. And that was from computer. So the problem here, of course, is that when you say you are going to glue these powerful components together, you're assuming that not so much the algorithms perhaps, but the data structures from the different components are very compatible. In fact, the algorithms in one component should be able to deal with the data from another and vice versa. So this, I think, is where the frustration comes in, where you find you do have very powerful components, but the gluing is actually not so easy, and it's a bottleneck that it takes a lot of time in getting the coding right, finding out how you can make it work, and also a bottleneck in that it might slow the computation down a long way, even though you have almost all of your computation is supposed to be done in the powerful components. A lot of it is actually spent in the connections between them. The Julian way is to write the whole project in Julia. So in practice, that doesn't quite happen. So if you look to the Julia, the code for the Julia language is very freely available at this website. And on the landing page, it shows you the languages that were involved in that particular package. And so Julia itself is written approximately 70% in Julia. And I think there are other languages which have similar percentages for writing themselves, but it's quite remarkable that a dynamic interactive language has so much. And differential equations, that I will talk about in 2 weeks' time, is 100% Julia. But this is a bit deceptive, of course, because differential equations uses, for comparison largely, not for basic solvers, it uses code from, say, sundials, and I think even from PyPy or SciPy, Python solvers, and it writes wrappers around them so that they can be called. Very often it's only for comparison purposes, but in some cases there are algorithms or C code, I think in particular in sundials, that differential equation just calls that code for its own solver as well. So this 100% is not necessarily the full story. Okay, so now we get to Julia's pride. So the first point, of course, being high speed. And here is the Celeste project. And let's see if I can get that up. Let me stop the share. So you can see if I can share. Oh, I think it's this one. I don't want that at this point, so I want this one. Sorry about that. So this is parallel supercomputing for astronomy. The speed is it produced at the time most accurate catalog of 188 million astronomical objects in just 14.6 minutes. Peak performance 1.54 petaflops, joining the petaflop club, which is it shares with Fortran C and C++. And these 188 million astronomical objects, they weren't known before the cataloging. Of course, many of them were known, but not by no means all. And it's a complicated, if you actually read the science, it's too complicated for me to attempt to convey what I understand about it in this talk. So we'll just stick with the 1.54 petaflops. It was obviously not sustained for the full 14.6 minutes, but it certainly happened very, very fast. Okay. Back to the talk. So that's the Celeste project. There are also these benchmarks, and I seem not to be linked, so that's why I have to keep dropping out. Stop the share here. I want also to go to those benchmarks. Where are the benchmarks? No, I don't want to go to this course. Okay, so these are the micro benchmarks, and they do an iteration method for getting pi as a sum, matrix multiplications, matrix statistics, the parse integers. I'm not quite sure what they all do. Mandelbrot, and so on. And here is the timings relative to C. So you see that a number of languages, Julia, Lua, JIT, Rust, Go, and Fortran, are all able to beat C on at least one of these benchmarks. But if they don't beat C, they're within a factor of a few small integers, 2 or 3 times the time for C. It's interesting that when you start getting to Fortran and Java and JavaScript, there's quite a few benchmarks that don't come below 10 times C. But once you go to the interactive languages, you start getting 100 or even 1,000 or more times the speed. Okay, so one obviously doesn't want to make too much of it, but it is definitely nevertheless an interesting thing. So it is hard to measure it. You can't, so just go by these anecdotal or just a few measurements, which could be very biased, it could be very specialized. And as an experience, if you wanted to not to have any sort of objective, but you just, what do people say, then you get lots and lots of remarks. And in Julia, there's a lot of very favorable remarks. If you look at the blogs and the conversations, you do get people saying, you know, I heard Julia would give such a speed up, but it didn't work for me. And then you would get people chipping in. And sometimes the conversation turns out well, the people coming in saying, but what did you do? You know, if you try this, you can really speed it up, and you get very satisfied customers at the end saying, yeah, well, I see now what I did wrong and why it is so much faster. But not always. I came for the speed and I stayed. Speed has never disappointed me. Okay, so in terms of recognition, Julia, the creators of Julia got the 219 James Wilkinson Prize. It's awarded every 4 years. You have to, your PhD must not be older than 12 years at the time that the award, I'm not quite sure, but anyway, 12 years. And Edelman, PhD, was much older than that. And the Sime News announcement was willing to say that you get the intuitive syntax of high-level code, doesn't mention the interactive or the dynamic versus the static, but basically say sort of also affirming Julia's claim of quick writing and high speed. In the rankings, Julia has climbed up, but it hasn't quite broken through into the top 20. It's one or two of the rankings, it breaks in there, but it doesn't stay. One interesting thing is that in the last two Stack Exchange language hated or loved, Julia came 5th twice, I think. And that is a measure of people, that's the number of people who say, I've been working in this language and I intend to keep working in it if I can. We've seen Celeste. CLIMA is a climate modeling alliance led by people at Caltech. And it's a very, very ambitious project, and it has done some really interesting things. One of the most interesting things about it is that it wants to integrate real-time data into long-term climate modeling, large-scale climate modeling. And it's an almost entirely a Julia project. The code for CLIMA is very, very much almost pure Julia. So what one sees is, and there are also some companies that are basing their whole business plan on producing Julia code. Relational AI and Pumas AI are trying to do the one. Pumas AI is pharmacological, pharmacokinetics and pharmacodynamics. And relational AI is a completely new model for dealing with databases. So it isn't really quite pure scientific computing anymore, but it is still closely related. So here is the claim of rapid development. So this is an analysis of person years spent developing and maintaining the languages, high performance languages, and it was obtained by using commit history. So if the same developer made 2 commits in 1 week, that was 1 person week of effort. And in that context, Julia taken less than 25 person years, whereas these other languages or implementations have had many, many more years of effort. So I don't quite know why Julia is so much smaller than these. There isn't really that much indication from the paper where I took this from, which is a 2019 paper. Benson, I've mentioned, is one of the founders. And the paper is called Dynamism, Julia Dynamism and Performance Reconciled by Design. I think the implication is that the very design of Julia has enabled very, very rapid development of code. It actually is really very much quicker to write the code in Julia that performs at a very high level, like PyPy and V8 and Hotspot, which are all high performance languages, I believe. I don't know any of them. Okay, I would say that DifferentialEquations.jl shows us also a remarkable output for low investment of programming effort. I don't know that any measure like this exists for it, but certainly if you look at where it started within months, within a year or two, it was already challenging for best in class, and it's just continued developing. So it wasn't that there was a huge army of coders at all. It was just that it was very, very quick for people to write highly performant code without really being experts in numerical analysis or numerical software. It's remarkable. Okay, so I'm going to show some examples of Julia's pleasure of Julia's code. Here I will just note a couple of high-level points. So Julia has taken lots of lessons from Python and MATLAB, especially, also from many other languages. And it's my impression that writing code in Julia is more of a pleasure than in either Python or MATLAB. When I started writing Python, I thought it was a tremendous pleasure. I had been writing mostly MATLAB at that point. I really enjoyed the difference. But I think that I started feeling some pain points in Python, and they increased, and Julia is really, it hasn't become more painful than I started when I did Julia. Okay, so I think that the ease of reading and writing code in Julia goes beyond the lessons that it got from MATLAB and Python and so on. It's not just that it took the best from those languages. It made this fundamental decision to use multiple dispatch in an obligatory way. And I think that that actually contributes in the end a lot to the ease of coding and the reading of code. Okay, so that's the items on Julia's pride. So let's go on to the charm. So the overview is that Julia is very straightforward to read and write and use. It's elegant, it's very interactive in a very pleasurable way. It's highly performant, it's very adaptable, it's very composable, it's very extendable. So this is what makes Julia into a really charming language, and why you find people doing really very pleasant things. So the REPL is what provides the interactivity, and I will see what I can do by showing you how Julia looks like in the okay, I think that'll do. It's I will leave and clear the screen. Okay, so most of the time when I start Julia, I just launch it from the command line. And you can see that it actually launches pretty quickly, not massively quickly, but it's there. So that's the standard hello world. So strings in Julia have to be enclosed in double quotation marks. A single quotation mark denotes a character, so you can have only one character between two single quotation marks. If you have A in single quotation marks, it's a character A, and if you have A in double quotation marks, it's the string that consists of the single character A. So it's also quite nice to do something like this. And as you see, Julia is actually puts in line breaks. If you put the line break in the line when you type it, and one can you can do string interpolation. It was 4 years from the start to the launch of version 0.0.0, then 5 years to version 1.0.0, and then another 4 years to today, which is version 1.8. So that's what it's like to interact with the Julia command line. It, of course, has the standard items like this. Sorry, not like 1 + 1 comes out with 2. But if I take 1 + 1.1.0, then you have a type conversion to floating point numbers. So in Julia, if you want to enter an integer, you don't put any decimal points. And if you want to enter a floating point number, you enter a decimal point. And we can either do that's how we write a complex number. And if I pass a complex number to the sign function, then Julia will just compute it for me and report to full accuracy. Okay, if you want to create a matrix or an array, Julia has actually got a tremendous amount of array facilities. It's one of its very strong points. But you can enter a MATLAB style array if you like this. And I can even just enter the things on one line like that. And now I can say A times B, and it's very nice like that. What is, of course, very powerful about Julia is that Julia has this very, very extensive and detailed type system, which I will use here. And I will say, when I input A, it must be of type matrix. And when I input B, it must be of type vector. And these are in Julia what are called abstract types. You get concrete types and abstract types. So these numbers we see here, they will be instances of concrete types. When I say matrix, A can now be any kind of concrete type that is nested or occurs in the tree of type somewhere underneath matrix, and similarly B for vector. And I say that is just A times B. And now I can say what is my mole of A, B. And I get the same answer, of course. But now I can say, well, what about 2 times B? And I get an error. So I've defined this as having a method for A being a matrix and B being a vector. 2 is not a matrix. So Julia does not read the singleton 2 by itself as a 1-by-1 matrix. It just reads it as a scalar. A strong distinction there. 2B, on the other hand, is perfectly well defined. So that's one of the nice things in Julia, where you can, if you've got, you're not allowed to start a variable name with a 2. And so when you have 2 times something which is clearly a known value of some sort, then Julia will usually allow you just to write it. So it looks a bit more mathematical. And I also want to show a little bit. So if I just create those 3 parameters, A, B, C, I can now define quadratic of A as equal to A times X squared plus b times x plus c, and I've defined a function. It's a generic function, meaning I can have, if I give it, I can have other function definitions using types that are less, that differ from the type A. I haven't specified anything here, but I can specify others that are more specialized. The type, oh, I'm sorry, I don't want to do that. I want to do this. It's still one method. I've just changed the, and now I can ask for quadratic, say 2. And it's 9, quadratic 22, 23 squared. What is interesting, however, is that I can have 22 plus 3m, say. So now I'm passing to the very same function, I'm passing a thing like that. And we will return to this in a little while. I can even try to pass quadratic a, and then I get a method. It says there's no matching for anything, but it says for element-wise addition, I can use broadcasting. So Julian has this very interesting possibility of broadcasting. So I can do broadcasting there and broadcasting there and see whether that works. Yes. So the problem with not using broadcasting is that just using a plus is a little bit ill-defined. And so because, yeah, so C in particular is just the number 1. And so you can't actually add the number 1 to the matrix, strictly speaking. But if you broadcast it, then it will take C times a square matrix C, 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 and add it. So this shows a little bit of the composability and the charm of Julia in that way. Okay. Now I need to stop the share and go back to the presentation. Okay, yeah. You can run your code files from within the REPL. You don't have to go to the shell. And interestingly enough, there are 3 further modes. And then because of the pain of switching in and out at this point, I'm not going to demonstrate them. They're 1 keystroke to get to the help system. There's 1 keystroke to get to the shell, and it's 1 keystroke to get to the package system. And you can basically ask for 1 item, for 1 answer on help, and then you go back to the Julia prompt. And similarly in the shell, you can give 1 shell command, you're back at the Julia prompt. And also in PKG, you can, no, PKG you stay. So if you give a PKG a query, or you want to add something, or you want to test something, or whatever, you can do all these things in PKG, but you'll stay there until you actually terminate your PKG session. So PKG is actually a very, very powerful thing. It's the package manager in Julia, and I'll talk about it a few times today and also next week and further on. Julia has Unicode. So as Francesco mentioned, you can just use Greek letters. This website gives you a very, very long list of the Unicode inputs that you can get. And it really makes things like this. So yeah, I would love to get to that. Let's see if I can. Where, there we are. Now let's hope that this comes up. All right, I think I'm on. There we go. Okay, so here you're using the symbolics package. So that's how you add a package, load it, define X, Y, Z as symbols. From linear algebra, you import the dot product and you import the cross product. As constant, you define just delta, and then you define a struct, which means it's a user-defined type which can hold values, but this is just a name. It doesn't have any fields, and it is just there to be able to dispatch on it, I think. And if you've done that, then, for instance, if you have a U defined using this vector of 3 combinations of symbols, then you get a message back when you evaluate that your result is a vector, and it's a vector of which the elements are of type, they're symbolic of numbers. And then you can have U dot delta and nabla, and you can it comes out all correctly. And in fact, if I keep on scrolling down, the Laplacian was tested and it became true. There are some other beautiful things that people have done. For instance, this one, if you have A plus A, then you get this little green box, so it's uniformly distributed. And if you have A plus B, then you get more or less the normal distribution, and so on. So this is a website which is full of beautiful things. For instance, this art. I should say that this one was posted. It wasn't created by the person posting it. They just posted it on from the Julian plot package. So this is one of the sort of boasting creations within plots, just to create this beautiful spinning heart. Okay, so back to the presentation. Okay, I want to go back to the REPL, and I want to create this. Is a single symbol. So this is the, well, it's not a single symbol, but it's a function with a name a alpha squared, and here's a function with a name alpha cubed, and alpha squared of x is x squared, alpha cubed of x is x cubed, and then I can test whether when I combine this with the square root, whether it comes out true. Here I create the cat icon, and I set it equal to 5, and then I take 2 times it. I want to just treat this as the name of a variable, and I hope that works. Okay, so let me go back to the REPL. Yeah. Okay, so in order to type alpha, I just enter alpha with a backslash, and I press the tab key. And then in order to get the alpha squared, so now that is, in a sense, a string. It's really composition of characters that form a symbol. And I can say of x, and I want that to be equal to x squared. And again, I have a generic function. Now I can go back and I can do uppercase 3, tab, and then x to the 3rd. And I have another function. And now I can say I want alpha itself to be equal to 22. So alpha by itself is just another, it's just another symbol. It's a name of a symbol that looks very similar to the other symbols that denote functions, but this just denotes the integer 22. And now I can say SQRT. So you can usually try a LaTeX abbreviation like SQRT, just backslash and then tab, and it does come up. And I now say slash alpha and slash super to the third. And there's my function name, and I now put alpha in there. That's the value of the argument. And I want to test whether that's equal to 22 to the power 3/2. So the double equation, double equal marks is equality testing that is type insensitive, and it comes up as true. In order to get the symbol cat, I have to do that. So one of the peculiarities of using Unicode is that every display system will have its own way of rendering a Unicode character. The Unicode that you see here is well, it's not really Unicode. Oh, sorry, you can't see that. So the cat symbol on the presentation was actually not created specifically using careful Unicode. It's font awesome's or awesome, yeah, font awesome or awesome fonts icons. I'm not quite sure what their relationship is with Unicode, but this is a legitimate way of creating a Unicode character in the REPL. Not all of the Unicode characters that Julia can handle actually reflect on my terminal. I don't have the right fonts for it in the terminal, but this one does. So let's say that's 5, and now I can say, and again I have to say cat test tab and enter, and then that's 10. So this is how Unicode is so very nice. And you get people who make tremendous use of Unicode in their code. And it's a bit frustrating if your display system doesn't render the Unicode symbols properly, but when it does, it's very pleasing. Okay. Come on. Okay. Right. So here is my REPL, and I'm running out of time, so I'm going to skip over this a bit. But my REPL is one of the many custom REPLs that you get. It will do a lot of color for you of your code, and it also has other services that make a role. I can't illustrate code LLVM too much either, but what code LLVM will do for you is if you pass it the code of a function applied to some argument, which is sufficiently concrete, then it will do a code, it will give you the exact code that is sent to the CPU, to the, it gives you the assembly. It doesn't actually give you the machine code, of course, which is very machine specific, but to a very, very low level, the output of LLVM that it will send to the system that actually assembles the machine code. And it's very, very interesting to compare apparently similar calls that give you very, very, very different, sometimes very long and complicated pieces of code come up that you really didn't expect. On the other hand, calls that you think would give you different code end up giving you the same code. Okay. Multiple dispatch is the crucial design decision in Julia, and I'll talk much more about it next week. But basically, generic functions with multi-methods are the default. Which method is selected depends on the type signature, which are the types in every field of the call signature, and this method selection happens at runtime, and it depends and it is determined by the values that you send to the function. And so in Julia, variables do not have type. It's their values, the value of the variable that has a type. And if you look at all these three together from, as I understand it, from the point of view of object-oriented programming, composition is privileged and inheritance is downplayed, and it seems to be superior. But I can return to that in the last talk, because it's not something that I feel is at all easy to settle. This business of type signature, what the users do is you define your code and your code body, and then you use user-defined types so that you call exactly the code body you have in mind. And this is the standard way at which Julia packages are actually built. So it's massively composable. I'm going to skip through this very quickly. Unitful allows you to define values that have a magnitude and a unit, a dimension. And this can just be handed over to differential equations, and it will just run. The code in differential equation doesn't require any modification, because Unitful has also for those values has defined the mathematical operations, and differential equations can just go ahead and use exactly the same code and get solutions which are Unitful values. Plots, however, cannot necessarily plot Unitful values. So what has had to happen is that there had to be a Unitful recipes addition extension to plots, and that defines new types and new functions. But then the three-way composition, where you define your values using Unitful dimensional values, you solve it in differential equation, you plot it in plots, and it just works. Okay, Julia has excellent package management. I really want to not go take too long, so I'm going to go. There's some very nice interactive notebooks. I would have liked to show you Pluto in particular. There isn't time for that. I found the people of Julia to be really, really warm, approachable, and responsive. But it tends to be in the Julia discourse and on Zulip, which is a Julia-specific discussion forum, and on the GitHub packages that are in Julia, much more than it takes place in things like Stack Exchange and Reddit and so on. There are two public faces. This is a little complicated. So there's the julialang.org, which is what you might think of as the open source aspect of Julia, but there's a Julia computing company, which in a certain sense is the same people, the core of the people in Julia Lang are the founders of Julia, and they're also the core of the Julia computing company. And many of the people who joined Julia very early on are still with Julia, and they are employed by the Julia computing company, and they're also very active in julialang.org. So it's a very interesting relationship. I think it works very well at the moment. There hasn't been any hostile forks of Julia or anything like that. And whether it will stay that way is an interesting question, but these people have been together since 2009. So something must be going right. Okay, here are the gotchas. You have to pay compilation costs. Most of the time it's not onerous. But recompilations can be a pain. TTFP stands for time to first plot. This can be several seconds and longer in Julia when you start plotting things. And it can be very frustrating for some people if they want to do lots of plots and they keep having to recompile. So there are workarounds, there are ways of dealing with it, there are ways of adapting your workflow so there's not too much of a cost, and it is improving. But this time to first plot and these kind of compilation, recompilation costs will always be part of the Julia language because they're inherent in the design. Okay. As far as I know, when people have made a concerted effort to get high performance. It has always happened. There doesn't seem to be any area of necessarily poor performance for Julia, but that's not to say that it is always easy to get. You're not guaranteed that your Julia code will run fast by any means. Very often it does. Very often you just very quickly rewrite your MATLAB or your Python code in Julia with minimal changes, and it runs much, much faster. Not always. But if you ask for help on Julia Discourse and places like that, the Julia community prides itself on being able to improve speed to within a factor of 2 or 3 of what is achieved in C. One of the real difficulties in Julia is that the error messages are really difficult to read. They can have enormously large type definitions, and they're also very long stack traces. You don't quite know where to look. And especially at first, they're very daunting. Another problem with Julia is its very large runtime. So freestanding apps and programs are difficult to distribute, but that seems to be fairly soon. That will be a much reduced problem, I believe. The tooling in Julia is better than it used to be a few years ago. The integration with Git is excellent, so you get good project management. There is profiling, debugging, and editing, perhaps not as good as it may be for the well-established languages, and the interactive offerings are also not particularly numerous, but they work pretty well. Large projects are possible, but I've seen claims that Julia as a language is not designed to be helpful in large projects, and there may be aspects of Julia's design which may be unhelpful. So far, the large projects have worked quite well. That may be due to the policies and the leadership rather than the language as such. Okay, so I've really rushed through this. I'm sorry today I misjudged how long an hour is. I couldn't speed up quite the way Julia can. But yeah, so the technical aspects next week, what exactly is multiple dispatch? How does it interface with the type system? And how does it work in terms of Julia's object model for handling values, and how does the homo-iconic aspects of Julia, which are very Lisp-like, and the macros in Julia, how does that all interact? And then DifferentialEquations.jl, just the very broad range of problems that can be addressed in that meta package. And how it's done, what the design decisions were, and how a relatively small group of people managed in a very short time to create an incredibly wide coverage of problems. And so I haven't really spoken enough about the two-language problem and the expression problem, so that will have to wait until the 28th of September. Okay, wow. Okay, so that's me done, Francesco and Ilya.
Yeah, thank you very much, Henri. It was a fantastic introduction to the Julia language. Thank you so much.